Yeah. So because graphing is so important in polar, at least when you first start out, that's why I'm giving a lot of videos on this, a lot of information. So our next stop is limicons, which is, I looked it up. It's actually a French word for snail, I think. And so the curves that you build here have, I don't know, some sort, there's a symmetry to it, certainly, but they leave a kind of curvy kind of path that a snail might take. Okay. Let's pretend. All right, so these are of the following form. And so an example might be r is equal to 2 plus 2 sine theta, like so, okay? And so I wrote the word cusps here, and there's going to be a story at the end of this how you can tell what kind of curve you're going to get. Okay, and we'll get to that in a second, but let's just plot a few points here and see what happens. This is the same kind of thing. You're plugging in points to find out where the curve is going. And this one is kind of benign. It's kind of cool because all you really have to do is go 0, and if I'm graphing it, I don't have to plot too many points. I just have to get its orientation, and then I know where it is because of the memory I have of doing this many, many times. Okay. But if I plug in 0, then r, it's different. It's shifted, isn't it? This is like, here's 2 sine theta, but then you're shifting. If this were rectangular, you'd go, oh, but it shifted upward by 2. And in fact, if you do the Stewart method on that, I just thought of doing that, why not? Shifted up 2 would mean your sine wave actually is here. This would be, let's say r is equal to 2, and this is theta. And sine, it starts at 0, so to speak, and the amplitude is going to be 2, but it's already shifted up 2, so it's really going to go 4 and down to 0 by the time it's done. So it's going to cruise up and down and up again, and at 2 pi, it finishes up. But look what's happening to r. R is actually starting out at 2. Now you can see that by going, when r is when theta is 0, r becomes 2 plus 2 sine of 0. Well, sine 0 is 0, so you get 2. And that's what Stewart's idea does. It says, I'm at 2. You know what's going to happen is it's going to increase all the way to 4 by the time you get to pi over 2. And that makes sense. If you plug in pi over 2, r is equal to 2 plus 2 sine pi over 2, right? And that's another 1, so you end up at 4. So if I'm lying, I'm dying, so to speak. Okay. All right, so we can attempt to graph this maybe, just to give you an idea of what's happening. It's weird that it has such large values, but try it anyway. So apparently, when you're aimed in the so-called 0 direction, you're not 0 at all, but you're at 2. Okay? And so when you go to pi over 2, now you're way out here at 4. Look what happens next in the Stewart model. When you go down to pi, you'd think you get to 0, but no, because of the plus 2, you're still hanging in there, and you're at 2 again. So when you get to pi, you're actually at 2 again. Okay? Notice I'm not writing -2 because that would be x. I'm talking r is 2, right? Okay, that doesn't look quite symmetric, but okay. And then finally, what happens is r keeps shrinking until you get to 3 pi over 2, and it's finally at 0. So by the time you get to 3 pi over 2, r keeps shrinking until you get to 0, but then r, see it? It's increasing back up to 2 again by the time you get to the 2 pi or 0. So this thing is swinging around the universe, and it's not a circle, is it? Because it's got a weirdness to it. But what happens is, as theta is swinging around this way, you increase to 4, then it shrinks back down to 2, and then as you go this way, it shrinks to 0, and then back out to 2. What does that look like? Well, it kind of looks like, I'll put this in red maybe. Looks like the following curve. Oops. Okay, maybe better than the following curve. Oh, that's pretty terrible. Well, okay, try it again. But you get the gist of it. Look at the bottom. That's why I wrote the word cusp. There's a cusp there. That's because it pinches into the 0 and then reaches out again. Okay? So theta is wandering all the way around, and it creates this kind of curve. Now, depending on whether it's sine and cosine, and whether the numbers are positive or negative, and who's bigger and all that stuff, you get different kinds of results. Okay? If you change this, let's do another one, and I'll do this, let's see. Let's change it to cosine, okay, and make it negative, and I'll change the size of the numbers as well. I'll go, another example would be r is equal to maybe 2 minus 3 cosine theta, and it's going to have a similar shape to it, but there are surprises as always. This is what I'm planning on right now, an inner loop one. That's good timing. So again, you would graph it. Now, if you do the Stewart method, which I'm starting to fall in love with a little bit, at least as a teacher's aid, I don't know about a student using it, we're going to graph 2 minus 3 cosine theta. In trig, that's tough. Okay, so, but if you go, it's going to shift up 2. That's 2 right there. That's this guy right there. But then it's going to be a reflection of cosine with an amplitude of 3. So cosine normally starts up top, but it's going to start down below this time at, say, -1. You can see that by, if you plugged in 0, you'd get r is equal to 2 minus 3 cosine of 0, right? And that gives you, what? -1, right? And you can see it here too. It starts there. And then cosine does its thing where it crosses. Let's see. Boy, I'm going to have a hard time with this. It's going to go up to 3 here also, isn't it? So that's going to be 5 up there total. Okay. So it's going to cruise up, and reach that guy, and then cruise back down again, and be at its low point again. And that occurs at 2 pi. And this is pi. And this is 0, and other places, other positions, like right about here where it crosses is pi over 2. My scale's pretty bad, and 3 pi over 2, and you can see what's happening. So there is a little bit, okay, of a negative value here, but it cruises to 0 by the time you get to pi over 2. Kind of tricky, isn't it? So here's where we're going to attempt to graph this thing. Okay, and so let's see. When you're pointing in the 0 direction, you're actually at -1. R is, okay? But then it cruises up to 0 by the time you get to pi over 2. Okay? Does it cross? It doesn't cross. By the time you get to pi over 2, you're actually at 2. So it goes less and less negative, and then by the time you get to pi over 2, you are at 2. So the angle is actually going in this direction, but you have negative values for r that will scope out a little loop here. At some point it's 0, and then it goes to 2. Let's follow the rest of this. It's getting a little complicated, so I'll just do this. By the time you get to pi, you're at 5. So when you're at pi, you're way out here at 5. And then when you get to 3 pi over 2, you drop back down to 2 again. And then finally, you get to 2 pi. And what happens is at some point, you turn negative again. So when you're staring at 2 pi, you're back at this point again. So what does the curve look like? It's an interesting curve, okay? What happens is you're negative, but then you cross, and then you go through this point, and you keep expanding larger, larger, larger. You hit this point, and then you're going, now you're shrinking smaller, 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 till you go through this point, and then shrinking to 0, and then you're negative, and you're right back where you ended. That's not a bad picture by Weber, by the way. Hold your applause till later. Okay, but that is an example of an inner loop, and it occurred because this number right there, the 3, is bigger. Okay, it's bigger than this number in the front, which is 2. So the end of this video, which is pretty much now, I wanted to go over with you what can happen, what the characteristics of a limicon are all about. Okay, so if you have, for example, first of all, we should talk about the following. So we're looking at r is equal to a plus minus b sine theta, or r is equal to a plus minus b cosine theta. Now let's just talk about the loops and the cusps and stuff like that. So I'll say if a is equal to b, and actually to make it easier for you, I'll just think, absolute value. If they have the same size, you have a cusp. That is, you have some sort of, it's cruising around, it cusps and keeps going. If it's upside down, if it looks like this, it's heart-shaped, and they actually call these cardioids. Okay, they're good for Valentine's Day, that kind of stuff. So graph yourself a cardioid for somebody. There you go. Okay, so if what we found, if A magnitude is less than B, then you have an inner loop. So it's going to swing around like that, okay? And then the other one that's, okay, if A happens to be the larger of the two, like you would have a 3 minus 2 cosine theta instead of the other way around, then you have a, I don't know, they call it a dimple. And so it just cruises, it kind of thinks about cusping, but it doesn't, and it travels on like that. That's the first thing to say. And then the rest of it is basically if it's sine or cosine. So if it ends up being like A plus sine, B sine theta, well, the orientation, you'll be able to figure this out if R is equal to that. We just did one, didn't we? It's up here. So the orientation of the thing is, let's say we're doing a cuspy one. Does that. Of course, if R is equal to A minus B sine theta, I believe that's the one that is the heart, like that. And then you goof around with R is equal to A plus cosine theta, which we didn't do. But we did do the R is equal to A minus B, I should put a B there, B sine theta. And in that case, we found it does this number. Okay, so this must be the one that does this number. Okay, so now you have everything you know about cardioids or limicons, so enjoy. And the next stop is going to be rose curves, and we'll spend some time with that too. All right, next video.